In this video, we're going to start talking about how derivatives can help us figure out what a graph looks like. So I won't quite tell you the meaning of the title right now, but by the end of this lesson, it'll be pretty obvious. So by the end of this lesson, you should be able to answer the following little question. What do the first and second derivatives tell us about a function's graph? And by the end of this unit, you should be able to answer the following big questions. How do we make finding derivatives easier? And what is the point of all of this stuff we're doing? Just as a reminder, in these last two lessons, we're kind of sticking more in that big question 3 zone. So like we're trying to apply derivatives to different situations. So let's start with the warm-up. Draw a function that is increasing and a function that is decreasing. So maybe I draw something like this and something like this. So this would be increasing and this would be decreasing. And what do you notice about the slopes of the tangent lines to each of your functions? Well, let's imagine I draw some tangent lines to this. So if I draw a tangent line there, maybe I draw another one there. We notice all of those have positive slope. And if I draw some tangent lines to my decreasing curve, so if I draw something like that, my tangent lines all have negative slope. And turns out that's not a coincidence. So it turns out that this is actually a test that we can use to determine if a function is increasing or decreasing. So if we find the first derivative and we find that it is positive on a particular interval, so if f of x or f prime of x is greater than 0 on an interval, then the function f must be increasing on that interval. Furthermore, if f prime of x is less than 0 or f prime of x is negative on an interval, then f has to be decreasing on that interval. So let's do a quick example. Let's draw a function given some constraints. So we're given that f prime of 0, f prime of 2, and f prime of 4 in this function are all 0. And we also have that f prime of x is greater than 0 if x is less than 0 or x is between 2 and 4. And we have that f prime of x is less than 0 if x is between 0 and 2 or x is greater than 4. So anytime you have a problem like this where you have a bunch of constraints and it says just draw a function, what I always like to do is translate all of these constraints into words that we can associate with the function. So like, for example, this second constraint, f prime of x greater than 0, tells me that this is increasing. So I'm going to write a little increasing next to that constraint. Likewise, f prime of x less than 0 tells me that it's decreasing. So that just comes from our test that we just talked about. So it's giving us some intervals of increase and decrease. It also tells us that the derivative is 0 at certain points, at 0, 2, and 4. So we can translate that to say that this is some kind of critical point, right? Because or critical number, I think we called it. Come on, eraser. Okay, well, we'll just write critical point. Oh, no. Oh, there we go. Okay, I thought my pen was out of batteries for a second. Okay, critical numbers. Okay, so what does this look like on a graph? Well, I think first we should break our graph up into the different intervals. So we have our critical points at 0, 2, and 4. So maybe let's label those. Okay, and those are critical numbers, so maybe we'll talk about what to do with those last. First of all, let's figure out what... Oh, okay, so we're not given function values, so maybe let's just... how do I want to do this? Okay, tell you what, how about we start with the second and third constraints? So we've put in our critical numbers. Now we want to just show that it's increasing. Less than 0 and also between 2 and 4. So maybe let's just draw a piece of curve that's increasing between 2 and 4 and less than 0. Okay, now let's do the decreasing. So it's decreasing between 0 and 2. So maybe I draw a decreasing curve between 0 and 2. And then also greater than 4. So then I decrease greater than 4. So actually, as I've drawn it here, and then I maybe just label these critical points, that is a function that meets all of our criteria. Okay? So that works. So, well, what can we do with this? So we've learned how to tell if something is increasing and decreasing, but we can go a step further with the first derivative test. So suppose that a number c is a critical number of a continuous function f. If f prime changes from positive to negative at c, then f has a local maximum at c. So not only does the first derivative tell us where a function is increasing and decreasing, but it can in fact tell us where we have maximums and minimums. So if f prime changes from minus to plus at c, then f has a local minimum at c. So when you're thinking of the first derivative test, you should always keep these pictures in mind. More so even than the mathematics or the symbolic phrases that we kind of just talked about. So when you look at the picture, to me, it's super obvious why this test is true. So in this first picture, let me change my color really quick. So if we're going from increasing to decreasing, or our derivative changes from positive to negative, we must have a maximum because we're going up and then back down. Likewise, in the second picture, if we're going from decreasing to increasing, or our derivative is going from negative to positive, we must have a minimum somewhere between where it switches, right? So those pictures to me make even more sense than the statement of the test. So keep those in mind when you're trying to remember these rules for certain problems. But we're going to do an example. So find the local maximum and minimum values of the function g of x is equal to x plus 2 sine of x. So the first step here is to find the derivative. So g prime of x is going to be 1 plus 2 cosine of x. Our next step is to find the critical numbers. So we need to know the points at which it could switch from positive to negative, right? So that's our next step. So we're going to set the derivative equal to 0. So we have 0 equals 1 plus 2 cosine x. And then I want to solve for x. So I can move over the 1. And then I can divide by 2. So we have minus 1/2 is equal to cosine of x. Now we need to go back and kind of think about our trig a little bit. So on the unit circle, if we're looking for a cosine of minus 1/2, that's going to be in the second quadrant, and it's going to be somewhere right here, right? Because this would be the small x coordinate. So that should be x is equal to 2 pi over 3. And, oh, okay, we get one more down here. So the other point we could have is 4 pi over 3. Okay, I should have specified here we want between 0 and 2 pi. So we're only worried about those angles on the first rotation of the unit circle. Okay, so we have our critical numbers. We have 2 pi over 3 and 4 pi over 3. Now we want to test our intervals using a sign chart. So I make a sign chart in a very specific way, and I think that this will help you when you get to more complicated problems. So I would suggest you do it this way. So we start by making a number line, and we put our critical numbers on the number line, like this. Okay, and then we want to test each interval. So the nice thing about a number line is it kind of has the intervals built into it. You don't have to think about them. we want to test each interval and see whether it's positive or negative in the derivative. Okay, so let's see here. So we have 1 plus 2 cosine of x. All right, so if we plug something in that's less than 2 pi over 3, like let's say 0 maybe. So if we plug in 0, cosine of 0 is 1. So 2 times 1 is 2, plus 1 is 3. So this interval will be positive. And maybe I'll write the signs in red just so that it's not blending in there. Okay, if we look between 2 pi over 3 and 4 pi over 3, maybe I pick the number pi to test. So cosine of pi is negative 1. 2 times negative 1 is negative 2, plus 1 is negative 1. So this interval is negative. And finally, maybe I pick something bigger than 4 pi over 3, like maybe I pick 3 pi over 2. So if I pick 3 pi over 2, the cosine of 3 pi over 2 is 0. 0 times 2 is 0 again, plus 1 is positive. So what I found here is I found that the first interval is positive, the second interval is negative, the third interval is positive. So from our increasing and decreasing test, I can interpret this to say that this interval is increasing, this interval is decreasing, and this interval is increasing. Okay, so if I want to find local maximums and minimums then, these will have to occur at these critical points. But we need to decide which is a maximum and which is a minimum, or maybe they're both maximums, both minimums. It depends on the function. But here, if we're going from increasing to decreasing, that means we're going from increasing to decreasing. 2 pi over 3 must be where the maximum occurs. Whereas, if we're going from decreasing to increasing at 4 pi over 3, this must be where the minimum occurs. Now, one kind of particular thing here is it's asking for maximum and minimum values, okay? So when it asks for values, that means a y value, okay? That what we've found so far is where it occurs, but when it says value, we really want the y value. So we want that actual maximum that it reaches, okay? So to find that, we take where our maximum and minimum occur, and we just plug it back into the function. So I can find g of 2 pi over 3, and that's going to be 2 pi over 3 plus 2 sine of 2 pi over 3. So that'll be 2 pi over 3 plus 2 times root 3 over 2, which is 2 pi over 3 plus root 3. So the maximum value is g of 2 pi over 3 equal to 2 pi over 3 plus root 3. On the other hand, the minimum value, I can find g of 4 pi over 3, which is 4 pi over 3 plus 2 sine of 4 pi over 3, which is 4 pi over 3 plus 2 times negative root 3 over 2, which is 4 pi over 3 minus root 3. So the minimum value is g of 4 pi over 3 equals 4 pi over 3 minus root 3. Okay, so that is how we find our local maximum and minimum values given a function using the first derivative. All right, the next thing we're going to talk about in this lesson is how to use the second derivative. And this is going to introduce a new concept called concavity that you may not have heard of before. If you've taken AP Calculus, you might have heard of it. Okay, my pen's acting up again. Come on, there we go. Okay, so concavity is the direction that a curve bends. So if we look at the pictures below, we notice that both of these curves are increasing. So both curves increase, but they bend differently. So we notice like one of the curves kind of bends to the bottom and one of them bends to the top. They're both increasing, but they're definitely different curves. So we need this different sort of measurement to distinguish between the two curves. And that's where concavity comes in. So concavity is the direction a curve bends. So this first picture we call concave up. And the second picture we call concave down. So the way I like to think about this, though, is concave up. We have our smiley face, right? So we got our smiley face here. And then concave down, we have our frowny face. So that's our little sad face there. So we have concave up are our smiles, and concave down are our frowns. Hence the name of this lesson, which is Miles of Smiles. All right, so now you know what the title of the lesson means. So there is in fact a way we can test to see whether a function is concave up or concave down, and if you expected that we might use the second derivative, you're correct. So the test for concavity, if f double prime of x is greater than 0 on an interval, then f is concave up on that interval, and if f double prime of x is less than 0 on an interval, then f is concave down on that interval. So just to summarize this in pictures, concave up, we have the smiley face, and that's positive. So smiles, positive energy, yeah, that kind of goes together. And then concave down, we have a frown, and it's negative. So that goes together as well, right? Because if you're frowning, probably negative outlook. So yeah, so I think the concavity test is pretty intuitive just because the signs kind of go along with what you would expect based on how the graph looks. So the one last thing to talk about with the concavity test is just like in the first derivative test where it told us maximums and minimums, the concavity test is also going to have something when we optimize the second derivative. We're going to find what we call inflection points. So an inflection point is a point on a continuous function where the concavity changes. So it's slightly different than finding the maximums and minimums. So like depending on whether it went from positive to negative or negative to positive, we got a maximum versus a minimum. However, with inflection points, as long as the signs change at all, so where the concavity changes at all, we have an inflection point. So for an example, let's look at this picture here. So if we look at point B, for example, we notice that at point B, the graph changes from concave down to concave up, whereas at point C, it changes from, let me do this in a different color. So at point C, it changes from concave up to concave down. But both of these points are still inflection points. And in fact, all of these points, so B, C, D, and P, are all inflection points. Okay, so just to reiterate, with maxes and mins, it does matter whether you're going from down to up to down, or plus to minus, minus to plus, however you want to view it. However, with inflection points, the direction does not matter. So all we're looking for is just any kind of change whatsoever. Okay. So I guess an example of a non-inflection point, so we can do that too. A non-inflection point would be this point right here. So notice we go from concave up to concave up. So this would be not an inflection point. And those examples are just as important as actual examples. We call them non-examples. Okay, so hopefully you understand what an inflection point is based on that picture. So let's practice another example. Let's find the intervals of concavity and inflection points of f of x is equal to x to the fourth minus 4x cubed. So first we want to find f double prime of x. So first we need to find f prime. So f prime of x is going to be 4x cubed minus 12x squared. And then f double prime of x is going to be 12x squared minus 24x. So we found f double prime. Now we want to find the critical numbers of f double prime. So we're going to set that second derivative equal to 0. And recall that when we're solving a quadratic equation, we can factor, and then we can set each factor equal to 0. So that's what we're going to do here. So I'm going to factor out a 12x, and we're left with x minus 2. So my critical points are 0 and 2. Okay, now just like with the first derivative test, I'm going to draw a sign chart. And I'm going to draw it like a number line and write my critical points on there. So we have 0 and 2. And once again, this kind of splits my number line up into the intervals that I'm testing. So let's see here. So I'll split this into 12x, x minus 2. So we're going to test each factor one at a time. And that's really handy when you have, well, in your case, when you don't have a calculator on the test. Splitting it into your factors makes it a lot easier to test for points. So let's see. So anything less than 0, 12x is going to be negative, and I'll fill out the signs with red again, just so that it's clear. Anything between, or anything greater than 0, 12x is going to be positive. Okay, I think we can agree on that. X minus 2 now, if we take anything less than 0, x minus 2 is going to be negative. Anything between 0 and 2 would be negative as well. So like if we took 1, for example, 1 minus 2 is negative. If we take anything greater than 2, that's when x minus 2 is going to turn positive. So if I want to find the sign of f double prime then, I just need to multiply my signs together because the function f double prime was a product of the two factors to begin with. So if I multiply negative and negative, I get positive. Multiply positive and negative, I get negative. Multiply positive and positive, I get positive. So this interval here is going to be concave up because it's positive. This one is going to be concave down because it's negative. And this one is going to be concave up. So let's write this as some intervals. So let's say concave up intervals are negative infinity up to 0 and 2 to positive infinity. So if it helps you on your number line, you can add those infinity points to the ends. That way it really reminds you what these intervals should look like. And concave down interval is going to be 0 to 2. So notice we always write these as open intervals. Because at those points of change in the concavity, so at 0 and 2, we can't say whether it's positive or negative, right? Because it's changing. So we can't ever include those points in our intervals. So those are always open intervals. And finally, we just need to find the inflection points. So remember, inflection points are anywhere the concavity changes. So both of these here are going to be where inflection points occur. Okay, so we're going to have an inflection point at 2 and also an inflection point at 0. So to actually find those points, we can't just use one number because a point is a set of coordinates, right? We need an x and a y. We have the x coordinates, we need to find the y coordinates. So for inflection points, we want to find f of 0, which is 0 to the fourth minus 4 times 0 cubed, which is just 0. And f of 2 will be 2 to the fourth minus 4 times 2 cubed, which is 2 to the fourth is 16, minus 4 times 8, so minus 32, and that's minus 16. So our two inflection points are 0, 0, and 2, comma, negative 16. So here are the answers to this question. We have our intervals of concavity, and we have our two inflection points. Okay, so that was kind of a lot in this section, but hopefully you notice that concavity and the first derivative test are really kind of the same test, just with a different derivative, right? So in both cases, these are both optimizing your derivatives. So just like we did in the previous lesson with the optimization word problems, that's all we're doing. We're just optimizing different functions, and somehow that tells us different things about the graph. So the last thing I want you to do is just check your understanding, make sure you can answer the little question. But other than that, this is the end of lesson 16.